In this video, we will use Kruskal's algorithm to find a maximum spanning tree instead. And technically, if you read Kruskal's algorithm, it is not built or programmed or written for maximum spanning trees. It's only written for minimum spanning trees. Because step one, it says to pick the cheapest edge available and continue selecting the cheapest edges. So obviously, that's going to find a minimum spanning tree, not a maximum. And actually, well, what's interesting is your book has a weird way of suggesting to adjust the algorithm to find a maximum spanning tree, and says what it suggests is that you change all of the edges to negative numbers. Then, if you apply Kruskal's algorithm, it will find you the maximum spanning tree. Because if they're like, and this is just a logic thing, right? If these are all negatives, then the smallest or the cheapest edge is technically the most negative, and we'd be selecting the negative 22 as our first selection. But I think that that's kind of ridiculous, from a common sense standpoint. And instead, we should just adjust Kruskal's algorithm. If we're trying to find a maximum spanning tree, just change it to pick the most expensive edge, and so on. Don't actually, if you're keeping track using notes, as I recommend, don't actually make that marking, but just kind of imagine instead of picking the cheapest edge, we're going to pick the most expensive edge available, then pick the next most expensive edge and mark it, and so on. Continue highlighting those most expensive edges, but the same thing, we can still not, we still don't want any circuits. So basically, we're going to apply exactly the same algorithm. We're just going to make sure that we only use the most expensive edges as we go. And so let's do it. Again, let's imagine we're going back to the original problem where we're trying to construct power lines, but instead of this costing the company money, it's going to instead make us money. And now our goal is going to be changed, right? Instead of picking the cheapest numbers, we're going to want the most expensive. We're going to want the most expensive connections instead. So we're going to start with the most expensive edge, 22. Mark that and continue marking the most expensive edges until we get to n minus 1 as our final goal. And we also can't make circuits, same deal. So next up would be 20, then 17. And again, as each edge that I add should be bringing new points together. Ultimately, all the points should connect together. 16, 15, they're going to be disjoint to start with, 14. But if we just keep plodding away, eventually we'll come back together. Notice here, the next edge, 13, is one that we want to skip because that would create a circuit here, here, and here. And so that would be a redundant edge that in our network. 12 here, 11 here. And again, we know when to stop when we reach n minus 1, or the way I like to do is just to see, are they all connected? And currently, 17 between U and S, these two vertices are not connected to the rest of the network. So, I'm going to continue going. 10 is the next cheapest edge until they are all in the network, right? And once I'm done, I've found my minimum spanning tree. And again, it should have 1, 2, 3, 4, 5, 6, 7, 8, 9, n minus 1 edges within it. And to find, the final answer is often going to be, well, what's the total cost of that? And in this case, that's going to be 126. And notice this is kind of an interesting last comparison to make between a maximum spanning tree and a minimum spanning tree, and why this sort of planning is really important. We don't want to just build random power lines between the city, because like I could think about my minimum configuration, which costs $46 million, versus my maximum configuration, which is 126 million. That's a pretty substantial difference between those costs, like nearly 300% difference, or 300% more, however you want to phrase it, 200% more, whatever. The numbers don't matter. It's a lot more, 3 times, whatever, as you can tell. And if we were to not put any thought into it, you could see why, planning is important and how this fits back into management science.